So far, we've only looked at rate conversion of deterministic signals, but sometimes we like to do a stochastic analysis of our system, so it's good to know what happens when we do up and down sampling of a stochastic signal. So downsampling works pretty much the same for a stochastic signal as it does for a deterministic signal. So if we have a wide-sense stationary stochastic process x of n that enters into a downsampler, we'll get a stochastic sequence out which is also wide-sense stationary. The problems occur when we do upsampling. So if we have a wide-sense stationary process x which goes into an upsampler, the upsampled version is generally not a wide-sense stationary process, and the reason for that is that the statistics of y of m are no longer shift invariant. So the reason for that is that some of the samples in y of m corresponds to samples from y of n, but some of the samples in y of m corresponds to zeros which are inserted in fixed positions. So therefore the statistics of y of m are not invariant to shifts in time. And this becomes a problem for the analysis we would use to our standard tools like periodograms and spectrum estimators and so on, which assumes wide-sense stationarity on part of the process that we're working with. Now there is a simple fix to this problem, and that is of introducing a random time delay in the interval from 0 to u minus 1, where u is the upsampling factor. So in the sense of doing that, we randomize the placement of the zeros uniformly in time, again making y of m wide-sense stationary. So this is not something that you would typically do in an actual circuit, but including it in the circuit for the purpose of analysis greatly simplifies the analysis. And this may be something that you've already seen if you've done pulse amplitude modulation for stochastic signals in the continuous time domain, where one typically also includes such a random delay in order to ensure wide-sense stationarity of the output process. So in terms of formulas, if we first look at downsampling and decimation, so the downsampling formulas look very similar to what they did in the deterministic case. So instead of getting relations between the output discrete time Fourier transform and the input discrete time Fourier transform, we now instead get relations between the power spectral density of the output and the power spectral density of the input. So the power spectral density of the output relates to the input power spectral density, just like the discrete time Fourier transform did to the discrete time Fourier transform of the input. So there is nothing new here. And we can apply the same thing if we do a filtering operation before. So we know that in order to do proper decimation, we needed to low-pass filter the signal in order to avoid aliasing. So since filtering enters with the magnitude squared in the stochastic case, when we look at power spectrums, we have to include the magnitude square also in the downsampler. But in the downsampling, we had an ideal low-pass filter with a unit gain. So this is equivalent to just including the unit gain filter, and we recover the original formula. And specifically, if you look into the range of 1 over 2 to the downsampling factor, so the range of frequencies that we can accurately represent in the downsampled signal, we have the same performance, that same result as we had in the time in the deterministic case, namely that the power spectrum of the output is just 1 over d times the power spectrum of the input scaled in frequency. And this corresponds to the discrete time Fourier transform formula that we had in the deterministic case. If we now look at upsampling, there is a slight change in the formula for what happens when we insert the zeros. So since the power spectral density is measuring energy per unit time, inserting zeros actually reduces the power of the signal, or the energy per unit time, since some of the samples, namely the ones that we pick from the input process, they will have the same power as the input process, of course, but the zero samples will have zero power. So overall, if we look at the power of the output signal, it will be 1 over u times this scaled version, frequency scaled version of the input spectrum. And this 1 over u is a factor which we didn't have in the case of the time in the discrete time non-stochastical deterministic case. So if we look at the proper interpolator, what would happen is we would have a formula just like before, but we would now include the filter magnitude squared, just like in the downsampling case. However, in the interpolation case, our low-pass filter had a gain of u, So we'll get a factor of u squared here, which will cancel this 1 over u and actually add a factor u. So if we do proper interpolation, the relation between the output spectrum and the input spectrum will be that the output spectrum is simply u times a frequency scaled version of the input spectrum in the range of frequencies up to 1 over 2 times the upsampling factor. And this is pretty much equivalent to what we had in the deterministic case. Consider now a case when we have a white noise process x of n, and we create two processes from that one. A higher rate process z of m, which is obtained from x of n through proper interpolation, and the lower rate process y of l, which is obtained from x of n through proper decimation. Then what can we say about the statistical properties of the higher rate process and the lower rate process? So can we say that both the higher rate process and the lower rate processes will both be white processes? Can we say that the higher rate process will be a white process, but not necessarily the lower rate process? Or can we say that the lower rate process will be a white process, but not necessarily the higher rate process? Or can't we claim that either the higher rate or the lower rate would be white processes in the general case? And the correct answer is option number 3. So generally, the lower rate process will be a white process, but not the higher rate process. And the reason for that is that picking away samples don't introduce any correlation between samples. So the lower rate process is a white process. But if we look at the higher rate process, we use interpolation in order to obtain that. And interpolation will generally introduce correlation among the samples that are jointly interpolated between two existing samples in the lower rate process. So therefore, in general, we cannot claim that interpolated processes will be white, even if the original process is white. And this is also something that we can see in the spectrum, where the lower rate signals spectrum would be completely filled by the spectrum of this, but where the higher rate signal spectrum would not be completely filled with the flat spectrum of the input process if we look at the formulas we had in a few slides ago. So to summarize, so rate conversion of stochastic processes is very similar to the rate conversion of deterministic processes, and we can use the tools that we learned in the deterministic case to a large extent in order to study systems from a stochastical process point of view. However, one has to be a little bit careful with the wide sense stationarity assumption, especially when one does upsampling. So generally, in order to maintain the wide sense stationarity, we need to introduce some random delays to re-randomize the stochastic process. And one should also note that rate conversion may introduce correlations where there are no correlations in the original input signal. And this is what we saw in the question.